Welcome to this explainer. Today, we're diving straight into something that is honestly a total game changer for digital preservation. It's an absolutely revolutionary system called DOS_restore. If you've ever wondered how classic games and ancient software are kept alive today, you are going to love this. DOS_restore is an automated system designed to transform ancient DOS binaries into completely clean, native source ports. And the crazy part? It does this without relying on human guesswork, fuzzy emulation, or hand-coded remakes. It literally mechanically extracts the true program hidden right there inside the original executable.
So here is our roadmap for today. We'll start with the lost shape of code, introduce the concept of the oracle, and then walk through the three key phases, going VMless, CPUless, and Memoryless. Finally, we'll cross the verification bridge.
All right, Section 1. The lost shape of code. Let's get right to the core problem. We all know that when a game is compiled, the original source code doesn't just, vanish into thin air. The logic absolutely remains. The computer still has to run it, after all. But the code completely loses its human-readable shape. We start with the dream, beautifully named variables like player position X and crystal-clear logic boundaries. But what the machine actually gets is a mess of raw assembler instructions, messy registers, memory addresses, and jumps. The loops, the file handling, the rendering, it's all still in there, but the human structure has been violently stripped away.
Historically, traditional reverse engineering is basically a giant guessing game. A programmer, or nowadays an AI, reads that raw assembler, forms a hypothesis, and tries to rewrite it in a higher-level language like C or Python. But honestly, it's kind of like guessing the translation of a dead language. It's incredibly slow and highly dangerous. A tiny mistranslation might not even crash the game right away. It might just subtly break a physics calculation 3 levels deep. DOS-Ray completely flips the script. It doesn't guess at all. It mechanically extracts the program to guarantee absolute mathematical accuracy before anyone even tries to understand the game's semantics.
Moving right along to Section 2, the original game as Oracle.
To get this kind of airtight mechanical proof, DOS-Ray relies on a massive paradigm shift in how we actually view the original executable. We have to stop looking at it as just a file to be decompiled. Instead, we define this original executable as the oracle. And the oracle isn't just a document or a static guide. It is the living, breathing game executing in a highly controlled, totally deterministic environment. Whenever the system needs to know what a function does, it doesn't guess. It runs the oracle and measures the exact result. It is the absolute, undeniable ground truth.
To actually make this work, DOS-Ray sets up this incredible custom-instrumented lab. And just to be clear, this isn't your standard emulator for playing games. It's a strict deterministic lab built for reverse engineering. By recording every single processor flag, every memory access, every sound played, and every frame drawn, we can strictly compare our newly generated candidate code against the oracle. If our new code produces the exact same observable state tick by tick when given the same inputs, well, we know for a fact it's mathematically correct.
But how do we represent all this extracted code? Well, the system decodes the assembler into a unified recovery IR, an intermediate representation. This IR tracks absolutely everything, from register liveness to memory aliases. And the amazing thing here is that the final output code is completely auto-generated from this IR. It's actually meant to be disposable. If an analysis improves, you don't go in and hand-edit the recovered code. You just throw it in the trash and generate a brand new, better version.
Now, let's map out the actual transformation process. We use 3 critical mechanical separations to free the game from its 1990s hardware constraints. First, Phase 1, going VMless. Then, Phase 2, going CPUless. And finally, Phase 3, going Memoryless.
Which brings us to Section 3, Phase 1, going VMless. Let's start peeling this onion. Phase 1 is all about removing the instruction interpreter. When a program runs in a normal emulator, there's a giant loop just fetching, decoding, and executing instructions one by one. In the VMless phase, DOS_ replaces this with directly executable functions in the host language. But there's a catch. Even though it's directly executable now, it still thinks like a 90s processor. It's manually moving data in and out of simulated hardware registers like AX and DX and using historical memory layouts. So the interpreter is gone, but the ghost of the CPU is still very much hanging around.
Next up, Section 4, Phase 2, going CPUless.
Here is where we completely strip away the emulated processor itself. And the structural difference here is huge.
That simulated global processor state, those clunky AX and DX registers, the manual stack pushes and pops, they completely vanish. Through automated liveness analysis and call signature inference over the recovery IR, DoosMara mechanically replaces all that processor state with clean native local variables and standard functional arguments. The code is finally no longer pretending to be a CPU.
But as we yank out the CPU, we still have to handle how the game talks to the outside world, right? So we separate the platform effects. A classic messy DOS interrupt, like an int21age for reading a file, is cleanly intercepted and swapped out for a modern API call, like platform.files.read. This completely isolates the core game logic from historical hardware quirks, putting it behind a really clean interface that you can plug into a modern desktop renderer or even a web browser.
And that leads us to Section 5, Phase 3, Going Memoryless. This is the final, and honestly, the most profound step of the whole extraction process. Now, let's be clear, going memoryless absolutely does not mean the program uses zero memory. I mean, that would be impossible. What it actually means is that the code is finally, permanently detached from that rigid, monolithic byte array memory layout of an ancient DOS PC. To pull this off, DOTSRI brings in some seriously heavy deterministic tooling. It literally watches how the program accesses data over time. By analyzing things like base and stride patterns or clustering field offsets, it automatically translates raw numerical memory offsets into proper native structures, arrays, and enums. So instead of reading some mysterious 16-bit integer from a random hex address, the code now clearly reads something like, say, enemy state equals attacking. The historical baggage is completely gone, replaced by a native data model.
All right, final piece of the puzzle, Section 6, the verification bridge.
But hold on, removing that historical memory layout creates a massive logistical headache. Remember the oracle? If our new native code uses beautifully structured modern objects, and the original DOS game uses a flat byte array, how on earth do we compare them to prove our extraction is mathematically perfect? Well, the ingenious solution here is the verification bridge. DOSRI automatically generates a translation layer that perfectly converts the modern native game state back down into the exact shape of the old DOS memory layout. This lets the system take a tick of the native code, bridge it back to the past, and prove it against the Oracle snapshot tick by tick. And the best part? This bridge is only for the testing environment. Once it's verified, the actual release build ships clean and native.
Throughout this entire journey, DoosArray operates on a very strict philosophy, summed up perfectly by this idea. The most dangerous state of reverse engineering is not a crash. It's a program that runs, but silently does something else. Normally, programmers absolutely hate crashes, but in deterministic reverse engineering, a crash is actually your best friend. A program that silently calculates the wrong physics trajectory is a total nightmare to track down. So DoosArray is built to fail loud. If it hits an unsupported construct or a memory alias it isn't 100% sure about, it doesn't guess. It just instantly triggers a massive, structured crash to protect the integrity of the code.
So, by shifting the paradigm from human guessing to pure deterministic mechanical proof, DOSStar proves we don't just have to emulate the past to preserve it, we can surgically extract it. We can peel away the hardware limitations of the 1990s and set the true software free as a pure native port. And honestly, it leaves us with an incredibly exciting thought to ponder. If we can reliably and mechanically set DOS games free from their past, what other pieces of locked-away digital history can we bring into the modern era next? Thank you so much for joining me for this explainer. I really hope this sparked your curiosity as much as it did mine.